So welcome back. So in the last few lectures, we have learned about PMMC type of instruments and MI type of instruments. And PMMC instruments, as the torque was unidirectional, you can only measure unidirectional flow of current, or they were mainly used for a measurement of DC voltages and currents. Okay, but MI instruments can accept bidirectional flow of current because torque is more or less directly proportional to square of the current value. So due to that, the torque becomes unidirectional irrespective of the direction of current flow. So MI instruments, although they are mainly used for measurement of AC voltages and currents, they can be used for measurement of DC values also. Okay, now, and in the second module we'll first see how to measure power and the importance of wattmeters. Okay, so power measurement, in the sense, there are two circuits. We know that they are DC circuits and AC circuits. So first of all, how do you measure power in a DC circuit? Measurement of power in a DC circuit is very easy, since just connect an ammeter and voltmeter. You can see in the circuit that, see, you have ammeter and voltmeter. Ammeter reads the current and voltmeter reads the voltage. Simply take the readings and multiply those readings, you get the power measurement. Okay, now here in this picture there are two ways of connecting voltmeter and ammeter. Here you can, the first figure, you can see that ammeter is very close to the low terminals, and the second figure, the voltmeter is very close to the low terminals. So what's the difference? See, whenever you connect measuring instruments, they will consume some power. Okay, take example the first case. This ammeter is very close to the load, that is low terminal. Okay, so this VA is the very small voltage drop across the ammeter. So ammeter carries a current I, and VA, that is the voltage drop across the voltmeter, is nothing but I into RA. Okay, so the voltage across, the power consumed by the load, that is VL into I, is equal to the total voltage V, which is being measured by the voltmeter, minus VA, the drop across the ammeter, multiplied by I. If you open it, we'll get it as VI minus VA into I. So the power consumed by the load is nothing but the total power indicated by the measuring instrument, that is voltmeter reading into current ammeter reading, minus the loss inside the ammeter. Okay, likewise, if we have this one, the voltmeter close to the low terminal, again the same thing happens. Here the current get divided, the total current we are measuring, that is I, get divided into IV and IR. So what happens? The power consumed by the load is nothing but voltage that is read by the voltmeter, multiplied by I into that is IL or IR here. Okay, so it is IL here, it is not IR, IL. So that is equal to V into, what is IL? IL is nothing but total current I minus IV. Okay, again opening, you'll get it as VI minus, or the power indicated by the instruments, minus the power loss in the voltmeter. So what I'm telling is that power consumed by the load is actually equal to the power indicated by the instruments minus the power loss in the meter. Okay, or what is the power indicated by the meter? The power indicated by the meter is nothing but the power consumed by the load plus the power loss in the instrument. So there are differences in two connections, but when the output is very large, this small consumption by the instruments is negligibly small. But if the output measurement is limited, or they have small values, then these errors due to the power consumption in the meters cannot be ignored. Okay, now how about the AC? So AC circuits, you cannot simply multiply voltage and current and say that this is the power measurement. Okay, so there we'll have a small thing which you have learned in the first year itself. So in AC we always talk about instantaneous power. So what is instantaneous power? Instantaneous power, P, is equal to instantaneous voltage multiplied by the instantaneous current. So let me discuss, as this is my reference, as voltage is my reference, it is actually Vm sine omega t I'm taking as a reference. That is why there is no phase shift. And where I is taken as, I is nothing but Im, that is instantaneous value I. Small values are always representing instantaneous values. So I is equal to Im sine omega t minus phi. So when I substitute this one, this is the case. Vm Im sine omega t minus phi is the instantaneous power. So why there is a phase shift or phase difference between voltage and current? Because current, it flows through RL circuit. Generally all the circuits are RL circuits. So the phase difference will be or the current will be lagging the voltage, not by angle 90 degree, but some angle less than 90 degree, that is phi. So here you can write, instead of omega, you can substitute theta as well. Okay, and if we apply the identity, what is identity? That is 2 sine A sine B is equal to sine A minus B minus sine A, so cos A minus B minus cos A plus B. If you substitute that, you'll get such a thing. And this is the expansion for the instantaneous power. And if you want to find the average power over a complete cycle, what is a complete cycle? Complete cycle is from 0 to 2 pi. So the base becomes 2 pi. Vn and Im are constant. You can take outside the integration and integrate with respect to theta. You can see that this has two components. If you open the integration, this has two components. We are integrating with respect to theta, so this component is a constant, whereas cos 2 theta minus phi, it's not a constant because we are integrating with respect to theta. But one thing is that if you integrate cosine or sine wave over a complete cycle, that becomes 0. So the second integration is becomes 0. So what happens to the first term? Cos phi also is a constant because we are integrating with respect to theta, that is also coming outside. So when you perform integration of d theta, that becomes theta. Apply the limits, 2 pi minus 0, that is 2 pi. 2 pi and 2 pi gets cancelled. What is remaining is Vm Im by 2 cos phi. Okay, and we know that Vm by root 2 multiplied by Im by root 2 is nothing but Vi cos phi, where V is Vm by root 2, that is Vrms, and Im by root 2 is nothing but Irms. So if we find the average power over a complete cycle, we will be getting the average power P is equal to Vi cos phi. Okay, now wattmeters are the devices or measuring instruments that is being used to measure AC power. Okay, now we have seen ammeters and voltmeters. Okay, and each had coils. Okay, in PMMC meters, we can see that the permanent magnet coil, the current carrying coil was moving, whereas in MI instruments the coil was stationary. The coil was stationary. Okay. Now here also, since we have to measure current as well as voltage, current has to go through a coil, and voltage also has should be measured across a coil. Okay. So we have two coils. One coil is fixed and the other coil is a moving one. Okay. And fixed coil is usually the current coil. Why? Because we have to carry, fixed coils have to measure carry large currents. So large currents in the sense many times the fixed coil is actually, this is the fixed coil, they are split into two. So when you have two circuits of current gets divided, and that gives a luxury to carry more current. Okay, and one more advantage is that as the fixed coils, as the current coils are stationary, there is no need to bring some other provisions to take in current and take out current. Okay, because they are stationary, you can easily supply current and take out current from a fixed circuit. That is why fixed coils or current coils are always stationary. Okay, so you can carry any amount of current, probably 100 amps current. That's a huge current that can be passed through the moving coil. Now the next one is the moving coil, that is also called as the pressure coil. Okay, so fixed coil is the current coil, the moving coil is the pressure coil, and the pressure coil is fixed or riveted riveted strongly on the pivot, and the pivot carries the springs. The springs will provide the controlling torque, and like I explained in PMMC meters, the springs are the current carrying leads to the coil or the moving coil here. Okay, so as the pressure coil is having very large impedance, so what happens? Negligibly small current is carried by the moving coil, so there is no problem in taking in that small current and taking out that small current. And being that much small current, springs can carry, hairline thick springs can easily carry those currents. Okay, so that is how the springs will serve as current in and current out for the moving coil, and they also provide the controlling torque. And normally the damping torque is provided by the air friction damping. They have a small aluminum vein connected across the aluminum, which moves in a sector shaped box. So when the pointer moves or when the pivot moves, they will actually provide the air friction damping. Okay, now we'll go to the theory of the electrodynamometer. We'll see how this equation is coming, which we'll go a little bit back, and then we'll come back then. Okay, so this is a very important topic, and we have to learn few things in wattmeters. Okay, and we'll go to the theory of electrodynamo type meters. Okay, so so this is the theory. So electrodynamo type meters are called as transfer instruments. Why they are called transfer instruments? See, calibration is required for any instrument. Calibration is required for any instrument. So these instruments, electrodynamo type instruments or transfer instruments, can be calibrated against a DC source. In DC source, you have standard cells as well as standard resistances. So it is very easy to calibrate connecting across a DC source, since DC standards are available. And after standardizing or after calibration, the same instrument can be used across AC source without any modification to measure the AC. Okay, so such transfer instruments are very important. They can be easily calibrated across the DC source by using the standard DC cell and standard resistance, and without any modification after calibration that can be used to measure AC. Okay, and the electrodynamo type meters are transfer instruments. Okay, now this is what I discussed earlier. This is the fixed coils or the current coils, which have two parts, and in between they have the fixed coil, which is nothing but the pressure coil. So pressure coil will actually handle the voltage across the circuit, and you know that is the pressure coil leads to the springs, and the spring will carry the current through the pressure coil, and spring will take out the current through the pressure coil. So the spring is actually a part of the pressure coil. Okay, however small, that much current is actually led into the fixed coil or the pressure coil through the spring, led into the pressure coil and led out of the pressure coil using those springs. Okay, now we'll just move through the operating principle of electrodynamo type instrument. Okay, and construction wise, moving coil is made of very thick coil, because they have to carry as large as 100 amps of current, but the pressure coils are made of slightly thin wires, because current carried is mainly limited to 100 milliamps. Okay, now so this is one is the fixed coil, that is L1 stands for the fixed coil and L2 stands for the moving coil. Okay, and I1 and I2 are the current, instantaneous values of current through the fixed coil and moving coils respectively. L1 and L2 likewise are the self-inductance of fixed coil and moving coils respectively, and capital M is the mutual inductance between fixed and moving coils. Okay, now we know that the flux linkages psi is nothing but L1 I1 plus M I2. M is the mutual inductance, that is due to the current I2. Likewise, psi2 is nothing but L2 I2 plus M into I1. And the total electrical input energy is nothing but E1 I1 dt plus E2 I2 dt. So what is E1? E1 is nothing but change of EMF is induced whenever there is a change in flux linkages. So E1 is due to d by dt of psi1, and E2 is due to d by dt of psi2. Okay, so if you substitute the values of psi1 and psi2 here, you will get this one. And if you open those, if you differentiate this bracket and this bracket, and you will get this term. Okay, that is what is the first term? The first term is nothing but that is L1 di square plus I1 into dL1 I1 square dL1. Okay, that is the first two terms. Likewise, that is here, that is I1 L1 di1 plus I1 square dL1, that is here, plus another term is coming here. We have again product here, that is I1 I2 dm plus I1 m di2, because these are the two terms we are differentiating. Okay, likewise this thing also can be elaborated or differentiated likewise. And what is the energy stored? Energy stored is nothing but half Li square, that is half I1 square L1 plus half I2 square L2 plus the energy stored due to the mutual inductance, that is I1 I2 m. Okay, now change in energy stored is nothing but differentiating these things, and we can open likewise. This is what you get. This equation is what you get. And from the principle of conservation of energy, the total electrical input energy is equal to change in energy stored plus mechanical energy. So to obtain the mechanical energy, you have to subtract equation 2 from 1. So we'll see the remaining in the next video. Thank you.